In this class, we will talk about FFT analysis, which is fast Fourier transform analysis, or FFT in brief. Like in the last class, you have seen that we have been able to store this digitally acquired data on the computer's RAM memory. So, from here how do we estimate or analyze the signal to find out its frequency components, okay, and that is what we will do. Well, to briefly review, we had discussed this in the past that even before FFT analysis was available, we could still estimate the frequency of the signal by signal filtering, by having analog filters. It could be band pass filters, low pass filters. Now, we will talk about octave and 1/3 octave filters later on when we talk about audio signals. And then we had discussed about signal heterodyning, wherein the phenomena of beat was taken into advantage to know the frequency of an unknown signal, provided we know the frequency of a reference signal. And then orbit analysis using Lissajous figure, wherein we can compare the ratios, frequency ratios of signals. And of course, mathematically, if the function is periodic, is mathematically describable, we could use the expansion of Fourier series as to find out the frequency content in the signal. For example, I should tell you when we do Fourier series, though, we had find out these coefficients A naught, A n and B n. So, A naught is actually independent on frequency, and this is known as the DC component of the signal, or what is known as the mean component of the signal. But because of the limitations of Fourier series, as if the signal may not be continuous, may not be periodic, etc., we have the Fourier transform, wherein Fourier transform can be in the forward direction from the time to the frequency domain Fourier transform, and if I have an inverse Fourier transform, I can get the time from the frequency domain. But this Fourier transform can be done mathematically because if you look at the signal x k, this is nothing but the digital representation of this transformation from the time to the frequency domain. I will explain you what this is, because this is an equivalent of the Fourier transform. And if you look at this equation, the integration has been replaced by a summation sign. So, this can be very easily implemented in a computer, and if the data, these are the x n is the digitally sampled time data, capital N is the number of data points digitally acquired. This n is what is specifying to the memory space in the A to D card. Small n is the time index, which goes from n is equal to 0 to n minus 1. So, it covers all the n data points, and k is similarly a small k is similarly a frequency index. So, this is in the time domain and this is the frequency components. Okay. So, let us see if you want to do this operations, and these are complex numbers and these are complex in nature. So, a real world time domain data will have complex Fourier or frequency domain components. Okay. And this computation is complex. So, actually what happens if you look into this number of operations, there are actually in this DFT discrete Fourier transform, there are n square complex operations. Okay. But in I am talking about before the advancement of computers, and you can understand to do n square complex operations, it was a Herculean task. Okay, talking about the year of 30s and 40s, during the World War, etc. How do you think people analyze signals? Okay, this is a very difficult task. Okay, I will give you a brief history of Fourier analysis. So, actually in 1964, two gentlemen working in the IBM research center in New York, known by gentlemen Cooley and Takei, they came up with an algorithm wherein it was not n square complex operations, but n log to the base 10 of n operations to do DFT. And in those days, computation was very expensive. So, but this when n square is a parabola with n log n, this is the n log n with n square computation time or resources. So, this was a much faster way of doing the same DFT, and this gave rise to a fast way of doing discrete Fourier transform, and this then came to known as the fast Fourier transform. Okay. In those days, what even today you are, the calculations you can do on your mobile phone and on your calculator were done in computers which are as big as this room. Okay. So, you can imagine the amount of computational effort required to do a Fourier analysis. Nowadays, on your laptop, if you do DFT or FFT, you will hardly know the difference between the computation time, and n could be as high as 10 to the power 12 or 10 to the power 14. It is not a problem. Okay. So, but in those days, in 1964, not very far off. Okay, but then this was the problem. So, actually to give a little more history about this FFT. So, this Cooley and Takei, once they came up with this algorithm, the company which we know, of the HP, Hewlett and Packard, they came up that is what we have read in history, that they hired Cooley and Takei and started selling FFT analyzers having the Cooley-Tuckey algorithm in them. So, they left IBM and they joined HP. HP started marketing the FFT analyzers from the late 60s, and they were very popular even till few years ago. But nowadays, we have chip based or card based FFT analyzers. Okay. Those days the FFT analyzers was size of a steel almirah, a large steel almirah. Nowadays the FFT analyzers could be as small as your cigarette lighter, okay, and they will be much more powerful, because such has been the advancement in electronics, okay, that fast chips, VLSI chips, etc. We can do this mathematical computations on the hardware very quickly and then come up with the FFT results. Okay. Well, so what is FFT? FFT is nothing but an efficient algorithm to do DFT, but what does FFT give us is very important, because to begin with I have a block of sample data 0 and to n. So, I have n minus 1 to be precise. I have this data which are there on my I am denoting them by circles, because this is what I have obtained after my data has been sampled. Okay. So, this will corresponds to each of your x n, and then I will have such an array of n data points, okay, and all I need to do is I need to sample it at a time index where n times delta t, where delta t is the sampling interval. So, I will n is equal to 1 times delta t, 2 times delta t, 3 times delta t, and then I will pick up all these successive values and plug it into the equation of DFT and do the operations using either the n log n operations or the n square operations, and come up with components which will be nothing but the Fourier components of such signal. So, if I was to now explain to you in a block diagram, I will have and I will get, okay, this is in time, this is in frequency, and this is the FFT process. Okay, so, this is the digitally sampled data, and this is the complex, and this is usually a real data. It is not a complex number, because real world signals are real, not complex, but I will have a complex, I will say Fourier or frequency components. So, XF being a complex, I can represent as okay, and this is in the frequency domain. But then I need to know what is the relationship between this time and frequency. For example, if I have n blocks of time data in the frequency domain, what happens? This is 0 component, it goes to n by 2 and maybe n by 2 minus 1, etc. So, these components will almost be a mirror image, and this is in the frequency and this is in the time domain. This could be sought in the negative frequency and this is in the positive frequency. For real world signals, we actually discard this data, we do not use this data. So, any n data point will give us only n by 2 meaningful FFT results. Okay. Now, so how do we relate to the sampling frequency to the maximum frequency contained in the signal to the spectrum which we get in the frequency domain? I should tell you, like we have time waveform where the x axis is the frequency, we call anything as a spectrum where the x axis is a frequency. So, this complex numbers which we will get, so the magnitude of this is nothing but okay. And then of course, there will be a phase between the real and imaginary. So, phase is nothing but tangent inverse of a phase is also a function of frequency. Okay. So, I am denoting through a magnitude phase or real imaginary. Okay. Now, we will see, before we see the relationship, let us see what certain terminologies in this FFT mean, and they all will relate to my original Fs, because we all know what Fs is, the sampling frequency, and we know how it was related to the feature, it is a property of the data acquisition card, and sampling interval related to this. If number of data points is n, total time t is nothing but n times delta t, this is nothing but the time record length. Okay. Because I have to rather do FFT on a block of sample data. So, this is my block of sample data. So, this is maybe I can either start with 1 and n, and then this distance between them is delta t. Total time here is n times delta t is equal to t. This is in time domain. Okay. Now, once we do FFT, this will be converted to the frequency domain, and let us see if I was to plot the results of FFT. Say, let me put the amplitude of this, and I am getting a plot like this, wherein I have joined all the frequency components. So, there are all these individual frequency points. I will not complete this, but so this is now not equal to delta t, but this is delta f, and which is the frequency resolution. There is a very fundamental relationship between this frequency resolution and time. They are inversely related. Okay. And the most important equation is this delta f is nothing but 1 by capital T. Mind you, it is not delta t, but capital T. So, the more the time you have, a long time instance, you can have very, very fine resolutions. Okay. You can imagine if I want to see frequencies every 0.1 hertz, 0.2 hertz, 0.3 hertz, how much of time do I require? Okay. So, because delta f is equal to 1 by n delta t, because t is equal to n times delta t. So, this is nothing but sampling frequency by n. So, if my sampling frequency is fixed I can have only a lower resolution or improved resolution if my n is large. So, large amounts of data needs to be taken to have a finer details of the frequency, and this is something you have to keep in mind while setting up your FFT analyzers to do the calculations. Okay. And then I hope this is clear to all of you, and then this is very important here how the frequency resolution is related to the sampling frequency and number of data points. Now, as I was telling you, once we have n data points, we will have one going from minus n by 2 to n by 2. This is the negative frequencies which we discard. So, the maximum frequency in the F max or in the FFT will be from 0 to this value is only n by 2. So, the maximum frequency F max which we obtained in this frequency is nothing but k times n by 2, and what is this k? I am sorry, delta f times n by 2, because each one of them is delta f. Okay. Now, delta f is nothing but f s by n times n by 2, that is equal to f s by 2. So, given a sampling frequency, I can very well almost obtain half of it. Okay. So, when I am talking about analyzing an audio signal out of a CD player coming out at 20 kilohertz, I should sample at 40 kilohertz and above. Okay. And usually, because of certain of these filters, they have a roll off, when I say a low pass frequency at FC, but because of this roll off, some data comes through. So, usually we sample at a value of 2.56 times F max. Okay. So, if n is equal to 1024 data points in the time domain, we will have 512 points in the frequency domain of interest to us. We will discard the few points at the last. So, we will have what is known as, when n is equal to 1024, n by 2 is 512, but we will take actual n is 400, and it is 2048, this will become 1024, this will become 800, and these are commercially known as lines of FFT. This means, in my FFT analyzer, I will only show you 800 or 400 or 200 data points. So, reference is an indirect way of telling that how much data I would have taken in my n. If it is 800, I would have taken 2048. So, nowadays there are analyzers wherein we can have up to 7200 lines of FFT. Okay. And this means 2048 blocks of data, data points in a block are taken and the FFT analysis done and the results displayed. Nowadays, FFT analyzers, I can either do it through the software given by that equation, or even implement it in a hardware where all these hardware computations are done. FFT computations also takes time. Imagine I have taken a block of data of n points. So, I have to do FFT on this. FFT takes some computation time. Okay. So, because if this is a continuous stream of data coming in, I am taking blocks of data, blocks of data. So, before I finish computing the FFT, if more data comes, I am going to either store, I have to either store them, otherwise I will lose the data. But if I can do the FFT, complete the FFT before the second block of data comes, I would have done what is known as the real time FFT. So, FFT computations are done on the fly, on the run, quickly, efficiently, before the next block of data comes to my block. Okay, and that is what is known as real time FFT. And then analyzer processing has to be very fast. Nowadays, the computers are very fast, so we can do it very quickly. And then there are softwares which will guide you to, suppose there will be a buffer management. In the sense, suppose you are taking more time, so this will come and hold this data somewhere till your FFT is complete and so on. So, this kind of management is done in a software also. Okay. But now coming back to this FFT, so maximum frequency which we can analyze is nothing but Fs by 2. Okay. Now, how do we ensure that the FFT which we have done is correct? Okay. For example, let us take the case of a sine wave. So, for clarity, I am drawing all the lines. Okay. This is contained in such blocks of data, and then I am doing an FFT. So, if this was a pure tone signal in the FFT, if I were just to plot the magnitude of this, it has, so I should be seeing one peak, okay, and this should be of 10 volt, and the frequency corresponding to the frequency of the signal, the magnitude of the signal. But you will see some instances what happens. I will go into the specific details. For example, this is of a frequency of 23 hertz. Okay. So, I should be having a delta f, and if I have taken delta f is nothing but your Fs by n, isn't it? So, if my Fs is say 1000 hertz and I have taken n as 100, my delta f becomes 10 hertz. So, obviously, this computer is going to understand 0 hertz, 10 hertz, 30 hertz, 40 hertz and so on. So, when it comes to 23 hertz, it is lost again, like we had in the amplitude resolution case, whether this is a 10 hertz signal, I am sorry, there will be a 20 here also, whether it is a 20 hertz signal or a 30 hertz signal. Okay. So, this is what is known as the picket fence effect. That means, I have inadequate frequency resolution in my signal. So, to overcome this, I need to have my frequency resolution very, very less. That can be done by increasing the number of blocks of data, number of lines of FFT. Same signal, if you do an analysis with different blocks of data or lines of FFT, you will sometimes get a sharp peak, sometimes you will not get a sharp peak. So, whenever you are looking for unknown frequencies, it is a good rule of thumb to have a finer resolution. If you do not see any frequency spikes coming up, you know you are not missing any signal, otherwise you are going to miss a signal. So, when you use an FFT analyzer, we have to be careful to play around with the signal, change the settings, see the number of blocks. Okay. How I can increase the block size. Of course, increasing the block size means more time, that well and good, but then I should not be missing any frequencies. There are signals, particularly when we have the space shuttle, etc., very massive bodies, there will be natural frequency of the order of less than 1 hertz, maybe one is having 0.7 hertz and that is 0.09 hertz. Low frequencies at so distinct and closely spaced frequencies. So, if I get a vibration signal from a space shuttle, I should be able to distinguish between 0.07 hertz and 0.09 hertz. So, this is a challenge to do. So, we have to have adequate frequency resolutions to ensure that this picket fence effect does not occur and we somehow miss the signal. This comes from the name of the English picket fence, in the sense, I don't know if you have seen the English picket fence there, white color pegs. Okay. People have it on the English side and there is the fencing. So, if I was to miss something, if I was to hit a cricket ball, cricket ball will pass if these fences are wide apart, these pegs are wide apart, but I will catch it if it is they are close by. So, this is what is known as the picket fence effect in FFT. So, once we have a finer resolution, we are going to catch the signal. Okay. So, this is to be avoided by having adequate frequency resolution by increasing the number of data points. Another effect of the FFT is what is known as the leakage error, and this has a serious effect in the amplitude estimation of the signal. For example, the FFT analysis, it takes a block of data and it assumes that this blocks repeats itself, assumes a periodicity. Okay. Because this data is coming, I have started sampling the data, I picked up the data, and when it comes to n data points, I stop it, I clip it. Now, if this data was a continuous sine wave, so if I put few windows here, I have sampled the signal by this red boxes, and you will see each one of this starts at a different and stops at a different amplitude location. Okay. For example, this has started here, this has started here. So, this creates an amplitude discontinuity. Okay. Now, to avoid this discontinuity, what we do? So, there is what is known as a leakage in the frequencies. So, if my actual frequency is this, the computer would estimate it as this because of leakage error. This is avoided if I multiply it with a function, a dot product, because this is the sample data, x. If I multiply x with a windowing function, wherein the window function looks something like this. So, at all the endpoints, it multiplies them and makes them 0. So, this discontinuities are avoided by multiplying it with such a windowing function, so that the leakage is reduced, and then we will get a better estimate of the amplitude. So, with windowing I will get as close to the, because here you see, because of the leakage my correct amplitude is given by this red signal x, but because of leakage I am getting this signal. So, this is a wrong estimation of the amplitude of the signal, and sometimes also wrong estimation of the frequency, because you do not know whether to take this frequency, this frequency, this frequency, and so on. So, a wrong estimation of both frequency and amplitude is obtained because of such discontinuities, because it assumes a periodicity. So, we multiplied with a windowing function to reduce this discontinuity, reduce the leakage, and get a better estimate. There are many such mathematical windowing functions, and I will write you the name of some of these mathematical functions. One is no window, or this is a rectangular window. Hanning is another very popular window, and this is a flat top. Then there is an exponential window. Rectangular window is for, it is actually a no window, it is just a rectangular function, and this is for a good frequency estimation of periodic signals. This is for a good amplitude estimation, and then this is for removing transients. For example, in the fourth example, suppose I have a signal wherein a lot of oscillations are there. So, I could put an exponential window like this, time domain. Okay, this is used for, for example, if I have excited a structure, I want to see its response would have died down because of the damping. I can reduce this ringing effect, so that I bring it to 0. Discontinuities are not removed or made to a minimum. And for periodic signals, we conventionally use either Hanning or flat top. If I want a good amplitude estimation of the signal, I should use a flat top window in the FFT. If I have to use a good estimation, in fact, a correct estimation of the frequency, I should use a Hanning window. Okay. So, in the FFT process, if I have taken care of this inadequate frequency resolution by increasing the number of lines of FFT or increasing the block size, I would be able to capture any unknown signal which would have otherwise would have missed. Another is to have a right estimation of either the frequency or the amplitude of the signal. A windowing function has to be used. Now, this FFT which we have obtained can be either represented in the, so this is a complex quantity, this is the real quantity and then imaginary quantity. This is the rectangular method of, so I will have the real part of x f and then imaginary part of, and you know how this f is related to nothing but k times delta f, where k is 0 to n by 2, k varies from 0 to n by 2, this is k is equal to 0 to n by 2. So, I will get the frequency spectrum both real and imaginary, and then I can represent them in the polar form like by the magnitude and the theta. Okay. Now, what does this convey to us? FFT physically, what does it convey to us other than the frequency of the signal? This signal also carries certain information as to the energy contained in the signal, as to the energy as a function of time, as to the power of the signal. So, from the frequency after the FFT, lot of post processing is done to this signal to analyze what other information we can obtain from this signal. So, let us see some of the signals, some of the quantities which we can obtain from this FFT. So, if this FFT has been obtained, I can obtain the linear spectrum. Magnitude of the linear spectrum is nothing but so unit becomes linear, and you will see magnitude means this is a real quantity. Okay. And another quantity which we use is the auto spectrum or auto power spectrum of the signal, sometimes power. This means it is defined by this notation x capital S x x f is nothing but the FFT of the signal multiply, be careful, this is a multiplication signal, by its complex quantity, conjugate, complex conjugate. So, this will boil down to, if I will not use the r I f notation. So, x r plus I x I times x r minus I x I. So, this will be nothing but, so you see, though the FFT is complex, the auto power spectrum is a real quantity. Okay. And linear spectrum is nothing but the square root of auto power spectrum. It will be just the square root of this, and which we have obtained here. And mind you, they are all functions of frequency. So, the auto power spectrum conveys how much of energy is there in that signal. Another related is the power spectral density. So, this is given by auto power spectrum by delta f. So, unit will be voltage square by say hertz, and this is used to characterize random signals which are varying with time. So, linear spectrum will nothing but the square root of power spectral density. So, this will be so this units will be voltage by square root of hertz. So, these are certain quantities which can be very easily calculated from the after post processing the signals, and this is just for one signal. But if there are two signals, we can find out the correlations between them and how they are related to each other. Okay. and many of the FFT analyzers will have these availability at the push of a button even in the softwares, but we should understand what physically they mean. So, we started with the signal x t, we have seen how we have sampled it, got the blocks of data x n, done FFT, got xf, from xf we have got s x x, and then we have got the auto power spectrum. Now, let us see when there are two signals, we will have what is known as the cross spectrum. Suppose I have two signals x t and y t, and usually in a mechanical system this can be very easily related to, suppose my input signal is x t, output signal is y t, and for a mechanical system to know the linear relationships between the signals, whether one is causing the other, to see the causal relationship between the output and input, I can look into many forms. One is the cross spectrum S x y as a function of f is defined as the auto spectrum of x multiplied by the complex conjugate of f, and you will see that this is a complex quantity. The power spectrum was a real quantity, but the cross spectrum between two signals x and y is a complex quantity. So, if I was to find out the transfer function or the frequency response function f r f, this is nothing but y of f by x of f in the frequency domain, because y of f is a complex quantity, x of f is a complex quantity. So, this is also a complex quantity. So, this will have magnitude and phase or real and imaginary part, because these are all complex quantities. So, now let us see how we can calculate the frequency response function from the cross spectrum and auto power spectrum. So, f r f can be written as y f by x f. This I can write it as sorry this means what? I have so the frequency response function can be computed as the cross spectrum divided by the auto power spectrum of the input, cross spectrum between the output and input divided by the auto power spectrum of the input. Okay. Now, there is another quantity which you have related. How are x and y related? Like in statistics, you must have studied about coefficient of correlation. If I plot x and y, if they are very close by, I will say they are nicely correlated in the time domain. Here also in frequency domain, we can find out a term known as coherence as gamma square f given by s x y f square divided by s x x f s y y f. Okay. And the maximum value of this could be 1. If I plot the coherence, as a function of frequency, this will maybe, if it is like this, I can say that at some frequencies the output is not because of the input. So, this has a very important application in machinery diagnostics, and we will see that in the subsequent classes as to how the estimation of coherence, frequency response function and cross spectrum can be used to understand whether the output y has been caused by x, whether a defect which is noticed in y is because of x. This can be found out by this coherence. And in machinery condition monitoring, when we measure signals from machines, we will be trying to find out the coherence between the input and the output, between two transducer locations, whether one is causing the other. And this is a very powerful way of diagnosing or finding the source of a fault. Okay, we will be seeing the applications of FFT in the subsequent classes, and this was just the basics about the FFT and how we can avoid errors in FFT, particularly the frequency resolution and the effects of windowing, and then what are the post processing features of the FFT which will be useful for machinery condition monitoring. And then another aspect of FFT is, I want to still with the available resources, I want to see much finer details, and that can be always increased, either you decrease the sampling resolution or increase the time record. Okay. So, sometimes decreasing sampling frequency may not be possible, then we have to increase the time record. Okay. Thank you.